So today we're going to talk about the properties of wildlife populations. And in class we went through the entire process of building a um, simple population model, which we're going to walk through again here in a couple slides. But for the most part, we're gonna go over what a lot of what we do in wildlife, especially our species managers, are dealing with the actual populations and the population processes to better manage them. So we should start out by at least defining a population. And what a population is basically any group of organisms of the same species that are occupying a particular space at a particular time. Now, that space can be defined on different levels. You can have that metapopulation dynamic where you have population of many smaller populations. So you're concerned about the overall population of a species that incorporates many habitat types that may or may not be connected at that given time. Usually, though, when we're talking about population, they are connected at some level. It may be a loose connection where it's a generational point in time where one or two individuals make it and transfer in between those smaller populations within each generation, or it's a constant flow and movement that's pretty unrestricted. Within a population, and the big part that we focus on whenever we're talking about determining the size of populations, we're focusing on characteristics of that population. And there's several of them, and we're going to go into them in detail. But what we usually do is we try to express them or quantify them in a statistical function methodology so that we can use those characteristics to determine or predict changes in the population or population structure. And those characteristics are really unique possessions of that group, that population, and not focused on the individuals of the population. So it's more of the average behavior or average characteristics within that group of animals, not on the individual level. And that's important to keep in mind. So if we were to build a simple population model, we start out by basically having n on the left here, that small n. That is the beginning population number at time 0. The things that go into a model, right, are if we're looking at the change of population over time, you have to assume that if it's any kind of population and at any kind of time, usually we focus on things like annual cycles or reproductive cycles to predict changes over the entire course of that reproductive cycle, or usually annual changes. So n+1 in this case is the ending population after 1 year. And what goes on during that time for most species is simply we have births and we have deaths, right? If this is a closed model, we have births and we have deaths. So animals aren't able to leave the population or enter the population. That's an incredibly simple structure. They get very complex, where you start incorporating things like immigration. So if the population is not closed, it's open. So you may have new individuals that come into it from other populations, or you can have animals leave it at emigration, which all alters the number of individuals within the population. That's separate from births and deaths. So it's really 4 different things going on here. So you have inputs of births, outputs of death. So subtraction of death, additions of births and immigration, subtraction of death and emigration. This can be expressed in this formula where it's just change in n. So the change delta n, change in population, is equal to the number of births plus immigration individuals minus the number that died and emigrated. That's as simple a population model as we go. You can make this as complex as possible by adding different properties to the model, and understanding the properties of a population and turning them into statistical functions allows us to predict and hopefully more accurately predict what the population will look at at a different time period in the future. Now, those properties are pretty wide ranging, and they need to be accounted for in some fashion. And we'll go into how we account for them here as we work through them. But in general, the properties that we're usually concerned about within a population are things like the density of individuals in a given area, dispersal rates, dispersion, and that's how an animal spaces itself out within a area or landscape, habitat, non-habitat, age structure of the population. So the older the age structure, that may have impacts on reproductive abilities. The sex ratio, if you have more males than females, that also may impact the ability for the population to reproduce and at the rate at which it reproduces. Natality, so functions of the youth, and mortality, functions of the death. So natality is functions of birth, mortality is functions of death. Also, we have basic growth forms and biotic potentials of different species. And we'll go into how that is linked to their overall species reproductive strategies as well. So let's start going through these properties. The first one we're going to talk about is density, right? So the number of individuals per unit area or volume in space. And the way we count this is basically one of three ways. The first, which almost rarely happens, is the idea of a census. You are able to count every individual that exists in the population and get a known amount. So you know exactly how many people are out there. We just went through the 2020 census. We made an effort to count every single individual citizen or person located in this country. So it's a complete count. An estimate, which is the thing we use most often, is basically a subsample of the population. So you're using some strategic method to get a representative sample of the population. With that, you get basically an average of the density over space and some kind of error function. So some measure of variation that occurs in that density over the space. But it is not that's 100% accurate. It gives you some measure of that error. Lastly, we have a method that gets used generally in combination with one of the other methods, and that's an index. And it's really a relative comparison. The actual number of animals is not known, but we do track the number that we have and the method of getting that number over time. So the method stays consistent, and we use that number as a measure, assuming that it tells us something about the population level. And I'll show you in a second how that works. So for the census component, the picture on the top right here is George Reserve up at the University of Michigan. And this is a fenced-in facility that every year they would go in and count the number of deer present in the reserve. And the way they did that is they'd get a line of people. They'd stand about 10 feet apart from each other and walk across the reserve. And every deer that would run past them, they would count. And they would know that because they covered every square inch of that area, they had to encounter every animal and then give them an actual census of the deer population within that fenced area on the reserve. So that's an example of a census in wildlife. Now, an estimate or a subsample, what they could do is various methodologies that we have that exist. For deer, we have things like aerial surveys, spotlight counts, distance sampling, and fecal counts. So generally what these are doing is they're following some kind of transect or known route that is representative of the habitat, but they can't sample all of it. And they count the number of individuals present on that route as they're doing it. It gives a mean of animals per unit area measured and a variance among those routes. The ability to sample and in terms of time and effort is kind of the big variation here for these methods. And that's generally the case for most methods. There are times where effort is really difficult. The amount of effort and time it takes to sample a population is incredibly difficult and therefore almost impossible to do something like a census. So you come up with these methods that allow you to get a representative sample of the population given what you know about the species. So they're using sometimes statistical structure to come up with that estimate. Now, that's examples of how that may impact population estimates are below, but usually we understand how they compete with each other and how they sit, right, in terms of their performance. And oftentimes we're linking multiple types of estimates together to get a better understanding of where that population probably truly sits. So you may use both a aerial survey and a fecal count just to understand. One is going to detect certain things better than others. So it gives you kind of two numbers to go off of it. It may exist somewhere in between. Now, the top left here, that image with lines going across are reserves, and that is actually the number of deer they count on their routes each year within those locations. So it is basically a spotlight route. They just drive along and count the number of deer they see. They use the same locations every year. They use the same methods. So they drive for 4 hours with a spotlight on weather that's this good about this time of year, and they just count deer. The assumption with this and how indexes work is that they're assuming that your ability to see deer doesn't change, and that the number of deer seen is really reflective of the overall population. So if you see less deer, the population probably dropped. If you see more deer, the population increased. We use this method with to inform deer populations a lot with roadkill deer. So we count the number of deer vehicle collisions in a given area or county or region, and we can incorporate things to adjust it, like number of miles driven by folks in that area each year, and assume that an animal is just as likely to get hit each year, and that basically it's related to the number of deer crossing roads is an indicator of population size, and the number of people driving isn't changing that much, or their characteristics of their driving is not changing that much to change the likelihood of hitting a deer if it's crossing the road. So that's an example of an index. So you track number of roadkill deer collisions over time is an indicator of population size. Other movements that are important to populations and understanding population levels are, we talked a lot about dispersal already in animal behavior, right? So that rate is calculated to determine immigration and emigration rates of a population. So if you know the likelihood of an animal to disperse in a given age range, you can account for, say, 20% of males will disperse over 10 kilometers, and that would get them out of your population. Then you know that your number of 1-year-old males by year 2 is only at 80% of what it was the year before, because 20% of them left due to dispersal. The same holds true with immigration. If you know how many animals are likely to come into a population from dispersing from other areas, then you can account for that within the increase of population, which may or may not counteract the dispersal component. You can't assume that immigration and emigration are equal, because a lot of times the movement of animals relates to habitat quality and competition and overall population levels. So if you are in an area that has a low population level with good habitat and not a lot of competition, you're less likely to have animals disperse and more likely to recruit new animals. So you can't assume they're equal. Now, we talked a little bit about excursion movements in the animal behavior component. Another term for that is called a SALI. And generally, we don't really care too much about these in the overall population model. However, the rate at which they happen does matter if you're trying to understand population levels or estimate a population and are counting animals. So if they go on a lot of excursions, you may undercount the population if the animals are not present within an area. And migration, we talked about already as well. you can model migration, but it becomes very important if you start trying to understand mortality rates related to migration movements, because animals moving through space generally have higher mortality rates than those that move less in space. Now, the next property is dispersion, and dispersion is basically just the pattern of individuals in space and time. So are animals likely to stay in regular uniform distribution in space and aggregated, right? So we have animals that are social and like to be near each other to go about normal functions of their behavior. Or do you have animals that randomly occur across the landscape? Now, how does that look in terms of visualizations, right? So random, you literally can have an animal appear anywhere in space. There's usually characterized by mutual interactions between individuals and between the individuals in the local environment. So they really aren't being tied to a specific habitat type. They can be found in most places. There's not a real need for one certain thing. So this doesn't happen often, but if it would happen, it'd be a very generalist species that it doesn't exhibit any kind of territorial behavior. Now you can get into regular distributions where you get into some antagonistic interactions between individuals or local depletion of resources. However, there has to still be resources available across the entire space uniformly in order for them to distribute themselves. Finally, probably the more common distribution that we have are these clump distributions, and there's an actual attraction between the individuals to a common resource, and there may be some antagonistic behaviors and interactions. However, the clumping to the resource or clumping to the individuals, it overcomes that at some level. Why does this matter? Well, if you're setting up those sampling regimes to estimate densities of individuals, you need to understand how animals put themselves in the landscape to correctly sample the population and area to estimate the density of the animals. All right, so let's get into a little bit about age structure and distribution. Age structure is basically the distribution of individuals among age classes. A lot of times we put age classes as years old, right? So we can look at that in terms of male, female, usually, right? So one side of the chart's male, one side of the chart's female, and you can track the percentage of the population that is as such through time and age. And why does age matter? Well, we usually have three different reproduction periods. We have pre-reproductive. So for humans, that's 14 and below. You have the reproductive period, 14 to about 40. And then you have the post-reproductive period, 40 and above. If you were trying to predict the movement of the population just by looking at one of these age structure distributions, you can get a pretty good guess, right? So you can determine that the one on the right, India, has a high likelihood of being a growing population. There's a lot more young that are coming into reproductive status, larger percent of the population, and therefore more than likely they are growing in size. Whereas if you look at France, it's a much more stable population. The percentages among age groups are pretty consistent. And if you looked at this 20 years later, you wouldn't probably see a whole lot of change in that pyramid structure. Now in India, you'd expect that would actually change. You may have changes in the actual reproductive structure of the population. Say if it decreases, if a certain cohort or group of cohorts decrease in population success, then you would see basically a bulge move up the population, right? So we constantly talk about our baby boomers. That was a bulge because there's a giant burst of reproductive success in humans in North America and in the United States specifically. And that continued up the chain as we progressed because it had to do with an event in history and in society. And that reproductive burst didn't continue to hold true throughout the next generation. So you can use these age structure distributions as a mean to understand a little bit about the future track that the population potentially is on without any changes in reproductive status or mortality rate. Remember that mortality rate will influence the percentage of individuals that are available in each bracket. So if you have a change in mortality rate where you have young that are succumb to a disease or older folks that succumb to a disease, you would see a pretty quick change in the percentage of the distribution if it affected only certain age structures. And what we usually have here is a stable age distribution is one that the ratios of numbers among the age classes remains pretty consistent across time. And a stationary one is one where they actually stay the same. So your mortality rate, your birth rate, all are the same across time. And therefore you would consistently see that same pyramid in 10, 15, 20 years, where a stable age distribution usually is all about the ratio, and you may still have an increasing population, but the mortality rate may be less, and therefore, older folks are living longer. Now, part of that pyramid also talks about sex ratio, right? So we see the number of males and number of females within each age structure. But if you took out age structure, sex ratio is still important. And it's usually expressed as either a percentage of males in the population, number of males per 100 females, or number of males per female. So a 1-to-1 male to female ratio is 50% male. And that matters, especially if you have polygamy or polygyny groups. It would help you understand the potential for reproductive output. If you have a population that's 70% males and then changes to 50% males, you have a lot more males in the population, or a lot less males in the population. You either added females or you had a male die off. And knowing the difference actually would help you predict how that may influence population. It can be impacted by breeding structure and age. Generally, in mammals, we see more males born than females, and it has a lot to do with fitness potential, and you have a lot higher chance of a male passing on your genes to the next generation than as a female. We do see some patterns in male-female ratios, especially in reptiles, where percentage of males in clutches is actually influenced by temperature. And we have two different patterns. We have one where if the temperature is lower, you have a higher ratio of males than females. And as temperature increases, you see much more females. This is the case with turtles. Now, in crocodilians, you see that generally the second pattern, where there's kind of this sweet spot for male production ratio. And if you are too cold or too warm, you get more females in the population. But if you're right in between, you get a higher level of males in the eggs. And how this plays in, like now with climate change, we would expect those that exhibit pattern 1 to have much more higher rate of females present in their clutches than historically has happened in the last 50 to 100 years for them. And the same kind of holds true with the crocodilians, depending on where that sweet spot starts falling on the temperature, right? So if your level at the top there, percent males, goes 2, 3, 4 degrees higher Celsius, then it's not going to influence them. But if they're already sitting right there at the cusp, then we'd see a drastic drop off in the number of males present. Now let's get on to natality. And natality is the inherent ability of population increase. So what is the recruitment potential of that population? So how many young can it bring into a reproductive status? And there's a few things that you need to understand. There's generally a physiological maximum ability of a species to reproduce. So that that happens under ideal conditions. They're not food stressed. They have ample resources. The temperature is suited to their physiological needs. They're efficient. Their metabolism's efficient, and so on. Then there's the ecological production of individuals. It's the realized actual production under existing environmental conditions. And this is generally a rate, right? Number of individuals per unit time. And in a lot of cases, we see the physiological situation, the maximum, happen in reintroduction scenarios where there is no competition for food resources. And once they reach that saturation point, that carrying capacity, which we'll get into in other lectures, you see a decrease in the actual natality rate. So the number of individuals produced over time come down and get to that eventually that ecological, the realized reproductive rate. And if you see the chart here, you can see where we introduced muskox in 1983, incredibly high recruitment rate, and that just steadily decreased for about almost 15 years. And we would expect it then to eventually, when it hits that ecological point, it'll level off. Survivorship. So this is basically a complement to mortality, and it's expressed as LX. So the number of individuals surviving to the age class X. Okay. And it follows usually 3 different survival curve patterns, where we have type 1, which is the top. That is a high natal survival rate, and that eventually hits a point where adults kind of have senesced, they've gotten older, and they start dying at a pretty predictable time frame. So high survival for both youth and adults. This generally is characteristic of a species that's long-lived and puts a lot of resources into single young or smaller clutches of young. The opposite of this is a type 3 species, where you have incredibly high mortality rates of young or young adults. And so you see a very drastic drop off, and the curve kind of slows down as animals age. They just aren't preyed upon or die as easily once they figure things out. And in between these two are kind of this flat curve of constant mortality rate, where young aren't overly vulnerable, not much more than the adults, and it just continues through time. So you have a pretty equal chance of dying every year. These usually in real life, and type 2, so the in between, still have high mortality rates associated with new young, but that levels off very quickly. And how these look in real life. So if we look at these survivorship curves between humans, which are incredibly long-lived, so so you get that slow drop that happens at the end of the curve, but really high survival at the beginning. As you can see that, majority of humans make it to about 60 years old. The Dall sheep is our type 2, so the red line, where it's pretty consistent, mortality rate from 0 to about almost 14 years old. That has a lot to do with the fact that they're in areas that predation is very difficult to occur on them, right? So they're on cliffs and not easily accessed by cats or even hunters to cause those mortality rates. Generally, hunters, even if they can access them, are after the 9, 10, 11-year-old sheep anyway, for the trophy status. So you don't see a whole lot of mortality pressure on the younger animals. And then, it's just access, and animals are equally likely to fall off a cliff if they're young or old, it seems. And then the opposite, so it's type 3, the mallards, waterfowl, where you have incredibly high mortality rate when they're young. And, at a certain point, it levels off. They make it through their first migration, that mortality and the survival rate goes up, mortality rate drops, and it catches up with all of them at like 6-7 years. And this is just an estimate. There are animals that live a long time, all the way till the end of, for ducks, 15 years is not unheard of. But these survival curves are pretty predictable of the reproductive strategy of a species, where you have R and K selection. R selection is one where you have an incredibly high risk of dying very young in your life. So you don't get to experience many reproductive opportunities, seasons. So when you do have one, you throw a lot of young out to maximize your chance of one of them surviving. So this is kind of the boom bust idea, where K-selected species have a very long, or generally long lived. So there's multiple opportunities to go through a good reproductive year. So you don't need to put a lot of young out, but you can invest a lot of resources in the young you have. So we fall into the K as humans, elephants, whereas those species that get eaten quite a bit or high mortality rate, many fish species, mollusks, clams, mice, and a certain species of mice. Rats are a little bit longer lived. Voles, waterfowl, all kind of throw into this. I need to reproduce as many as I can this year because there's a good chance I don't have another opportunity. All right, so that's the idea of survivorship curves. Now, mortality is just the idea of how many animals or individuals are you losing from a population. So that excludes the emigration component. This can be very difficult to measure. And usually we spend a lot of time trying to understand this number and rate. And basically it's calculated as, dx, the number of dying in age interval, x to x plus 1. So the chain is mortality rate. So the mortality rate is equal to that LX, that number of animals in population 1, minus the number of animals that are in population 2. So this is looking at how many animals did you lose. That is the mortality of those animals. And if you want to get the mortality rate, so this DX calculates the mortality number, QX is the mortality rate. So QX is simply number of animals that died, so DX, so LX minus LX plus 1 over LX. That's the mortality rate. And we would generally mark this against things like growth rates, population levels, to understand whether or not certain events are happening within a population at years of age. For instance, the mortality rate we know in many ungulate species, because they're hunted, changes based on their age. So for a hunted population of red deer, you can look at the survival curves of males and females, right? So QX, the mortality rate. And for males, within these two different populations, one of the population has a small constant rate, mortality rate, all the way up to about 7 years old. The other one has a high calf mortality rate, but as soon as they get a year old, they had no mortality up till the age of 6. And all of a sudden it spikes. Why does that happen? Well, both of these are hunted populations. So the hunters are targeting that age class of 7, 8, and 9 because the antlers on the animals are the largest at that point. When they hit 10 there, what ends up happening is that mortality rate drops because they are no longer trophy animals and probably not pursued by the hunters, but they still have mortality associated with disease, old age kind of ideas. So eventually it hits, 1,000 animals are dead. But the majority of the animals that die within the population are that 7, 8, 9 age class, because that is the trophy animals that the hunters are after. The rest of the mortality rate is associated with natural disease causes. And this is pretty consistent across many of our ungulate species. Now, if we look at that type 2 curve and the species of sheep that I mentioned that have that likelihood of not really being vulnerable, we can see that despite both sheep being in 2 different places and hunted, because they're really not very vulnerable to access from hunters, the male and female mortality and changes in population are pretty consistent across ages, and their survival is consistent. All right, that's an overview of the properties of wildlife populations. You want to make sure you understand all these different properties, the definitions of each of the types of properties, and how you may calculate them, or how they may influence your understanding of population change. We'll have our review session on Thursday, and our lecture exam number 1 is next week. And this is the last lecture prior to that exam.